Well, thank you very much for having me here today. It's great to be back in person giving these talks for the CAV group. And again, my name is Jose Palacios, and I am, I guess, microphone. Get closer. There you go. And I am somewhat, I guess you can call me the lead of this group, which is populated by a very, very capable group of people here listed on the board. And something I would like to remind the group is that you get a freebie one day of consulting, right, if you need any assistance with any of your research. So I highly encourage you to contact us with anything we might be able to help. And also I would like to remind you that myself as an experimentalist, that day includes a potential day of testing. So very cool capabilities for the group. So really fast, let me introduce some of these gentlemen. You have work going on in terms of piezoelectric actuators and deployable structures. That will be from George Lesiert. From Chris Rand, you can do all kinds of different activities that you can read here on the board. And again, the group continues passing through myself, which I'm going to list some of those in my presentation coming up, and other of us in the group. I would like to remind you that Ken Uchino actually retired recently, so unfortunately we've lost some of those capabilities, but I'm sure he'll be willing to answer questions if you reach out. I know he does for me. And with this, let me go ahead and introduce the new group, because the good thing about the university environment is that we always have new blood coming in with new ideas and new assistants. So really fast shout out to Professor Ning and Professor Greenwood. You just saw some of the content from Professor Greenwood. And they're doing some pretty neat stuff in terms of multifunctional deployable structures. And Eric is working. I don't know what that's not showing. There you go, slow. Working quite a bit on acoustic testing, and it is a great pleasure that I'm actually working with him on some of that. I guess I can say that you're my partner in crime, literally. So with that, today I would like to introduce myself, some of the things we do from my specific group. And in that front, I guess my hat will be an experimentalist. So anything that has some experimental component, I think I might be able to assist. So let me go through some of these different tabs that I get my hat switch on. We do quite a bit of structural design for testing. So for example, one of the projects we were working on has been the Dragonfly. And this is not quite too related, I get, to adaptive structures, but certainly related to design of structures. So we have assisted with the design of the blades, and we have already conducted some half-scale wind testing at the 14x22 NASA wind tunnel. And we're very excited that we're going to go with a full-scale blade. These are 1.4 meter blades, coaxial configuration, to the TDT, Transonic Wind Tunnel at NASA. Heavy gas, try to reproduce somewhat of the aerodynamics that Eric Greenwood was talking about. You cannot run these things, when you're trying to match Reynolds numbers, for example. So a little brief on that. Here I can show you a video of actually a full-scale configuration that we already tested. This is not at the TDT, obviously. This is in one of my chambers, so it's not aerodynamically comparable. But I can start playing with what the loads do, right? What kind of vibrations am I going to have to deal with on those arms and so on. So anyway, that will be my structural design testing hat, which now I'm going to go ahead and switch. If this moves forward, we want to move forward, please. There you go. So before I move forward, actually, I have another cool photo to show you. This will be a 10-foot diameter rotor that I shapped into my hover stand facility. This is actually a rotor from a Joby vehicle. You can Google what the Joby vehicle looks like. Point being, this is certainly not an aerodynamic test, right? This is a rotor in a box that is going to make a tremendous mess. But this test was actually an icing test. Okay, so at that point, once I started creating ice to the rotor, I don't really care much about the aerodynamics. So I thought to show you that photo because the next tab I wanted to talk about is not the icing yet, but remember that rotor. I'm going to talk now about rotor performance, which we do a lot of balancing, acoustics, and aeromechanics. Okay, so if we go ahead and look at the acoustics, this is now still in some of the facility photos I work with Eric Greenwood. Some pretty nice capabilities there. If you're going to be in the short course, I'll show you all of these details tomorrow. And if we look into, let's say, balancing, that's the topic of the presentation today. Okay, I'm going to focus on adaptive structures, and we have developed a very neat passive balancing configuration that adapts to the vibration of the system to get rid of that vibration. So that will be the topic today. So I'm not going to brief these images because I'm going to go through them in detail in the presentation. So let's go ahead then and start this presentation. I got to give a shout out to my students. Really, they are the guys that make me look good. Lots of work done by Ahmad Haidar, currently working at Leonardo. He started this topic. And later, Ryan Blessington continuing the work. So I'm going to brief some of their work today. And again, the topic is passive balancing. So your washing machine at home works on that principle, right? When you put your clothes on and all the clothes end up on one side and the machine goes supercritical, meaning post first resonance frequency, water on a surrounding channel goes opposite to those clothes to balance the system. So on that same concept, we decided to develop an adaptive balancer that will assist us with these imbalance events. And imbalance events, I'm going to show you, there could be multiple. You could be thinking about a jet engine that loses one of the blades, or let's say that the blades start getting eroded asymmetrically. So that will introduce vibration to your jet engine, for example. Rotorcraft. Rotorcraft are not supercritical in general. But now that we start talking about this smaller eVTOL, the rotors are becoming supercritical. And if you want super smooth flight for whatever mission you're doing, you could potentially introduce these passive balancers. So let me go ahead and give you a brief introduction. Again, you're going to have some eccentricity due to some imbalance. And the whole goal is to get rid of that vibration only when we are supercritical. This system will not work pre-resonance, and I'm going to explain why that is. So in my specific case, if you remember, I have a hat that is aircraft icing, right? So one of the big imbalances I deal with is ice shedding events. I'm flying the V-22, one rotor sheds one blade, the other two didn't shed. Now I have a huge imbalance on that rotor, right? So V-22 will not work because it's not supercritical, right? But if we will have a smaller vehicle with the same configuration, for example, right? We would like to have a smooth flight even though we have ice shedding events. So let's go ahead and look at how this eccentricity works. And again, this only works, right, once you are post first resonance frequency of my system, okay? Before resonance will not work. So let's explain that really fast with some images. Pre-resonance, okay, if I have some imbalance, and I look at what my forces acting on some masses around the imbalance. So the whole concept is to have these free traveling masses around the eccentricity, okay? We're replacing the water on the washing machine with masses that can move on a track. So you can clearly see that pre-resonance, 0 degrees, right? I'm on the blue box. My masses are going to go with the imbalance because I have a zero phase effect on that mass, right? So I'm going to make things worse pre-resonance if I have these masses freely moving around. Now, if I am post-resonance, post-180, the opposite happens. You see that now my forces are actually going to push the masses against the eccentricity, potentially balancing the event, right? If this clicks forward, go forward, there you go. The mass will go against the eccentricity, and now I have a balanced system. So if we can introduce these free masses moving around that center of rotation, and I have a sudden imbalance, I can bring the system back to balance really nicely, right? So that's kind of the goal. This is what we want to develop. And obviously with applications to rotorcraft, right? That's my biggest hat, I guess, rotorcraft applications. Again, as the vehicles become smaller and smaller, eVTOL, you're starting to potentially be able to have supercritical conditions. And by the way, this is the rotor, the 10-foot diameter rotor I showed you in my facility. That's that vehicle. It was a very, very neat set of tests. So with that, and obviously jet engines, right? That would be the beautiful application. Those are all supercritical. Okay, so skip. Let's talk about partitioning. I told you that if I have these masses around a track and I am pre-resonance, until I reach the resonance, I'm going to make the system worse. The masses are going to go with my imbalance, right? So to limit some of those effects and to also limit cycles that might occur through transition, we put partitions. So that way we do not allow all of these masses to make it really bad as I go through resonance, okay? So that's one of the tricks we learned through our modeling, which I'm going to brief really briefly. So let's go ahead and show you what will happen without partitions. Subcritical, all the masses make everything pretty bad. But if I have my partitions, I'm going to limit those negative effects pre-resonance. So that's lesson number one that we developed for this technology. Supercritical, obviously, you're going to go against the imbalance, and you're going to make the system better. And we're going to show you all this with high-speed cameras if this works okay online. Okay? So the objectives, again, is to develop a passive balancing system, and the case study that we focused on was ice shedding events. And this is very useful for us in the lab specifically because we run a lot of shedding events for different testing. So having the capability to balance my system allows me to run many hours of ice shedding for the customer. Okay? But again, that's not the only application. So with that, I'm going to flash at you the mathematical model. And the reason I put this on the slides is in case there is somebody really interested on these topics. You have the slides. You can go through the equations. You can most certainly contact me or go through some of the publications. But it's a very comprehensive model, which we have taken into account the flexible shaft, we have taken into account the friction of the balls, the centrifugal forces, of course, all the dampening that could happen between the rotation on the balls and the track. There's a lot of components that were not taken into account in the literature that have a massive effect on how you model and design the systems. If you ignore some of these factors, you will get potentially the very wrong answer, right? And I'm going to actually show you what happens when you use the wrong modeling, because our first passive balancer that we designed for my facility was based on literature equations. And we ended up with a balancer that didn't work, okay? It was only when we introduced friction on the balls traveling on this track that we were able to come up with a configuration that actually was applicable. So with that, let me flash you some energies, okay? So we're using Lagrange's equations, right? Trying to come up with the equations of motion. We're taking into account all my energies, and you can probably add even more terms. We're starting to consider now the fluid in the track, because I believe we can do some pretty cool things if we change the fluid from air to something else, right? So again, just flashing those at you. We understand Lagrange's equations. We're taking into account all the normal forces, the centrifugal forces, the friction, the rotation of the balls, the deformation of the track, okay? And all of those are going to show up in these equations, which end up in a model. So again, I don't want to spend too much time on that because I only have 30 minutes for this, but I can show you what these mathematical tools end up doing. So we have now 3 graphs over here. The one on the left is no masses. Okay? So you are already expecting that guy to be pretty imbalanced because we don't have any solutions. The one in the center is basically the same system, but ignoring friction. And you're going to see how critical it is to actually throw friction into the system. And then a third graph which takes into account friction. So let's go ahead and pray that this plays. Seems like it's playing. I see some motion on the bars. Is it playing? Please play. Is it playing? This is the problems of running things from online. It should be playing. We're not going to be able to see it. Hold on. Hold on. Let me go back. Okay, I see. Okay, is it working? See? It's loading. It's getting stuck. Now go back. Somebody push me back. All right, it's not loading. Let me explain what will happen, okay? We're not going to be able to see these videos. That's too bad. If you have these presentations, please download them and check them out because it's pretty exciting stuff. What you will see is you will see tremendous vibration on the one without the masses. Then on the MATLAB solution, you will see even larger vibrations without the friction. And you will see that the friction system ends up with a solution that is different than the one without the friction. Okay? And I don't know why it's not playing, so I'm not going to spend any more time explaining it. What's that? Yeah, but you should be able to see those masses moving around. I don't know why it's not playing on the presentation. So in any case, take my word for it. See if you can download those and see the videos, and you will see how important it is to take friction into account. So now we're going to go ahead and move on to our specific application, which is trying to make this work on the icing facility. Again, the rotors will accrete ice, the ice will shed, and eventually we want the passive balancer to take over. So the facility, the first balancer that we designed, again, was done without taking into account friction on the system. And we came up with this configuration that told us that it was okay to put the balancer under the rotor, told us which diameter we should use, right? And we ended up having issues with friction because centrifugal forces will take over at a specific size of the balancer. And the balls will get stuck, and they won't be able to roll around the system freely, right? So the size of the balancer becomes extremely important related to the friction, which comes from the centrifugal loads, right? So right there, I already ended up with a system not working because I used the wrong assumptions on my models. So before we run to the actual configuration, I do want to show you what happened with a system that didn't work. So this is the balancer that we fabricated, has the masses traveling around it. You can see the partitions. You can see how it goes below my rotor. And here, this will be a high-speed visualization video of ice accreting to the blade and then shedding, okay? And again, we might not be able to see any of these high-speed videos given the internet connection. We had a high-speed camera up above, so what I was doing is looking at the positions of these balls as they would move relative to my system. And the point is that these balls, right, on the high-speed video will just not change position even upon a shedding event, which create an imbalance. Again, friction took over, centrifugal forces will not allow these masses to move. So we did have a really good correlation, actually, once we developed the proper modeling tools that showed us what the system would do. And again, the experimental results gave us an accuracy on the model that was very favorable. Vertical axis will be your steady-state force amplitude versus your mass imbalance. But again, the performance was very small, right? These masses barely moved because they were constrained by the centrifugal loads and the friction. And you can see here on this graph that my force amplitude basically didn't really change upon shedding events. The stars will be your shedding event, and you can see how the balancer, in some cases, even got worse, right? So you can see how the peak actually became a higher loading, higher force, even though the balancer should have taken over. So these high-speed videos, which you are not going to be able to see in this presentation, will show you how even at subcritical speeds, when I move on to supercritical speeds, my masses just don't move. They're stuck, right? Again, too big of a system, too many centrifugal loads, the masses cannot move. You had the wrong design because you used the wrong equations. So this, again, will be a high-speed video. You will see the system move around that point, okay? And nothing to see because the masses were stuck, right? So this high-speed video wouldn't help me with anything. Now, let's use the right equations, take into account friction, and design a system that will actually allow me to balance. You can see, well, let me go back. I'm going back. I'm showing you too much. How now, based on these equations, we got smart and we figured out that putting this balancing system farther away from the boundary conditions will actually give more inertia to the masses, which is very good. Also, we became smart and we realized that if I make this too large, centrifugal forces will overcome my capability to move the balls. So there is an optimal position in terms of the sizing for those masses. Also, we got very smart, and since friction is very smart, or very important, let's not use metal against metal, because it's pretty high friction. Let's use something with low coefficients of friction, okay? The other thing we saw on the first system is that ice will get into our balancer, and the balls will get frozen in place. So we also encased everything to prevent it against ice formation. So you see a photograph of the new balancer, and now you can start to see how my model, even though my accuracy went lower, and it makes sense that my accuracy is lower because now I'm dealing with very small values, right? But you can see in blue how the new balancer actually brings my vertical axis, which is my steady-state forces, way down, right, compared to my imbalances. So very neat design. And my performance went from 8% to 80%, right? In fact, 8% plus before, I was making it worse, red, to negative 80, blue. Nice design for a balancing system. So this is really the chart that says everything. You can compare to the prior one if you remember, right? Every time you see a shedding event in red, you can see how my vertical forces drop down to almost nothing. Again, this is on the supercritical regime. You can see on the 50-second on the time how I'm going through resonance. As I go through resonance, this is not great, right? Because, you know, through resonance, you're going to go into limit cycles that are going to make the system vibrate quite a bit. And I'm going to tell you how we think we can solve that. So supercritical, we're great. When we're running tests in the lab now and we're seeing shedding events, we are happy. Back in the day, we will shed something and the building will shake, okay? So again, that's my transition point. This is too bad. This is too bad you're not going to be able to see this because this is high-speed visualization of where the masses go subcritical, 500 RPM. I might tell you that the resonance frequency of my system is 900 RPM. So once I pass 900 RPM, you will see a steady state compensation of the imbalance. So 800 RPM is my transition. The transition is really neat because this is the area where you cannot find solutions to where these masses go. So they start dancing around quite a bit, right? And then make the system vibrate pretty severely. Yeah, I don't think so because I have it automatically to start with my click. It's a problem with the bandwidth, right? These are very large videos embedded on the PowerPoint, so they won't play unless we download it. But it's okay. You understand that these balls will be moving, right, quite severely on this high-speed visualization. And if you are really interested, please go ahead and download that presentation. This will be another high-speed video, okay, with a strobe visualization that will actually show you how these balls are moving with the imbalance. And you will see how it moves around that red point, right? So you can see, or you will be able to see how the system is very imbalanced on the spin up, right? So that's the spin up. And eventually, once you go through transition, you will see how the system becomes nice and happy and is perfectly balanced, okay? Once you pass the 900 RPM. So initially, you will see some motion. Through transition, it will get crazy. And then you will end up with very nice zero vibration. This will be now the perfect steady state condition at 1200 RPM, where you will see how the masses are going to compensate whatever imbalance I have on the blade. Okay? So flashing images, because you're not going to see them because it's not going to work. But this, again, will be a strobe light with ice in it. You can see how I have ice on top of the system now, because I will be spraying a cloud. And what will happen here is a piece of ice will shed. And then you will see a sudden motion of those balls against that ice shedding event, and the system stays balanced. Okay? So it will be like a split second. Like on one frame of the high-speed camera, all of a sudden you see these balls move against the imbalance. So it's pretty neat. Too bad you cannot see it. But take my word for it. So with that, I don't know how I'm doing with time, because I was going to spend more time on the high speeds. But let me move on to the conclusions. We have been able to design a balancing system that has brought me from a reduction to almost 80% of the vibration with respect to a shedding event of very large masses. Okay, we're talking about huge imbalances here. We have developed the model to be able to come up with these configurations. And right now, we are working on improving this from the point of view of the engineering application. I told you that as I go through resonance, this is not good, right? I do not want to go through resonance and have to have worse condition that I would have if I didn't have the masses. Even though, as supercritical, you get me better, I still don't want to sacrifice my system every time I go up and down. So what we're working on is we're working on a clamping system that basically, on the first spinning event, you will be just as bad as always, right? The first time you spin it. But then once you get to the perfect condition on supercritical regime, right? Imagine these balls have found their magical spot. On the way down, the clamping system, which is CF-based, centrifugal clamping, will hold the balls on that magic position. So now you come down perfectly located. As you go back up, you are now perfectly placed, so you do not have any of the vibrations. Once you reach RPM, centrifugal takes over, the clamps release, and now your balls are okay to prevent you from any imbalances due to transient events. So to me, this is a good definition of an adaptive structure. Okay? Certainly adapts as you are changing your imbalances. We're also working on trying to implement this to multiple systems, because what happens now when you have two rotors on a single shaft, right? What do we call the first resonance frequency? Do we have multiple modes? Can we make this work on what frequency regime? So it gets a lot of fun in terms of the mathematical modeling. So with that, I believe I have time for questions. I'm going to go back and see if we can see at least the coolest one, which I think will be this one. Let's see if it loads while you guys ask me questions. If it loads, great. If not, we'll call it a day. Yeah, this is why this whole Zoom thing is not ideal, right? The old computer here with the flash drive was the way to go, but that's okay. Any questions?
Okay, questions for Jose?
Are your own students allowed to ask questions? Go ahead.
First, quick comment, Jose, it's a GIF, so if you download the presentation, the GIF will play. It's not going to play over internet. It's not a video.
Okay.
So quick question, because I had an interview with Rotor yesterday, so that's a feedback from industry. We are using the small deflection assumption here, but again, the force that's going to drive your balancer is kind of proportional to your deflection, right? So should we consider maybe using different models to, to verify the passive balancer?
I think the deformation is already taken into account in the model. As you'll see, the new design of the balancer did not end up far away from the boundary condition for no reason. It ended up where the deformations are maximum, right? It's not only a load issue. On the original models, we were only considering the forces. And that was the wrong assumption, because physically, if you put a balancer right next to a boundary condition where nothing is moving, right, you're not going to have any effects on those masses to move around. The farther away you put it away, right, where you have maximal deformations. So the point being is, if we're going to be placing these balancers on a long shaft inside of an engine, right, because this is the perfect application. An engine is a hollow tube shaft where we have real estate to implement these masses. So you're going to place them at the antinodes, right, not close to the nodes. So you're right, the deformation is a critical factor to take into account of where to put these balancers.
Okay, we have a question from Gary.
Yeah, you said to control the friction, you avoided metal-to-metal contacts. What did you end up using?
So that was just some ABS plastic with very small surface roughness, straight out of Amazon, nothing fancy, okay? Like, we didn't have to go crazy in terms of the friction. We just wanted to avoid metal-to-metal friction on the system. And with a very small change on the friction, we realized that, you could make it work. In fact, by simply making it smaller in radius, we couldn't make it work even with metal. So the friction only becomes critical once you reach that specific point where the centrifugal force is just, it's a 1 or 0 type of thing, right? So you don't need to go with anything, like I said, too fancy in terms of the friction.
Thanks.
Yeah, no problem.
Okay. Anybody else? All right, and once again, we'll try to make sure these briefings are available for download. I'm not sure they are right now, but we'll look into that, and hope you guys can have a look at the videos.